Thanks a lot. Thanks everyone for attending the talk. So as some of the previous talk already mentioned, so after the modeling step for the physical science problem, we actually want to do this sequential experimental design to gather data so that we can minimize the acquisition cost. So this talk will be focusing on this direction in general. You can actually see from the slide here, I'm going to focus more on this Bayesian approach for modeling, and in particular, I'm going to talk about Gaussian processes. So when we're actually thinking about an interactive machine learning system, there is an experimental designer who actually actively propose new experiments to perform, and it interacts with the environment, which could be embodied by the physical environment, like the wet lab experiment for doing chemical engineering, for example, or a computation oracle which does these expensive simulations for the physical phenomenon. It could also be interacting with a human expert who conduct experiments in a sequential fashion and provide feedback to improve the system as we're doing more and more experiments. So in order for the AI system to make a decision or to propose this informed decision for human experts to carry on, we first need to have some kind of model to model the dynamics or like the environment, which we call the hypothesis space. And in order for the experimental designer to interact with the environment, we also have to have access to an action space, which embodies like this large space of actions that it can actually perform and to act upon the information that it gathered. Furthermore, in order for the experimental designer to be understood by the physical environment, by the domain expert, we also need to follow some interaction protocol so that the interactions between different modules actually make sense. So in this talk, I'm going to focus more on this modeling and active learning part, which mainly focus on hypothesis space and action space. So when we think about like a hypothesis space in the physical science environment, actually it could be huge, right? And so what actually amounts to, for example, a Nature publication will be some preliminary results that is based on some simplified assumptions of the nature. And but those results are usually not immediately applicable. So if we have some actually final product we want to deploy in the real world, there is a large distance between the preliminary model and experimental results towards the real goal. So there's this large exploration step before we actually reach a stage where we can safely deploy the problem in a real world experiment, and that process is usually very costly, involves huge amount of money and time investment. So our goal here is basically to use learning-based approaches to expedite this process by learning from previous data and experience that the machine has seen before. All right, so again, to recap, I'm going to focus on like the hypothesis space and action space. I'm going to talk about like complicated hypothesis in experimental design, which appears in a number of physical science problems. And I'm going to introduce a few examples of algorithmic insights, basically informing us what is the best or optimal actions that we should propose in order to have a principled framework for information gathering for decision making. So in the following of this talk, I'm going to concretize the problem via a few applications in a number of domains, ranging from protein engineering, nanophotonics in material science, and to some like control-related problems where we're trying to gather information in order to make the most efficient decision for a particular task. I'm going to touch a little bit upon these cosmic experiments, which is like one ongoing project which we're doing at UChicago, which is very exciting for me to give a sneak peek of the general direction and goals for the project. And there's a little bit of 3D printing, like in the mechanical engineering domain, where we apply sequential decision making and Gaussian process optimization to minimize the storage efficiency, to maximize the storage efficiency and to store the minimum of data in order to actually predict the physical phenomenon for the heat transfer models. All right, so I'm going to give you a very brief refresher on the basics for Bayesian experimental design. And the framework basically starts with interaction, right? So if we have a model, and we have an input space X in the capital X, modeling all the actions that the model can perform. And there's some underlying black box function F, which we want to model, but we don't have enough data for that, so we have a prior on that. At every iteration, the Bayesian experimental designer is asking for labels for a particular data point, which is one action. The environment returns the label, and it does this interactively. And the model, on the model side, we maintain a posterior distribution over the hypothesis, and we're actually seeking for the most efficient data point to maximize the information regarding the posterior. And so that brings us towards this Bayesian or black box optimization problem, where we're trying to optimize a function. And that function could be thought of as a fitness function in the domain, for example, for robotics and control, which is the response for a particular input signal. From material science, it could be like the physical properties of a particular material. I'm going to give you a few concrete examples later on. And for structure hypothesis, we can think about application in biomedical or biochemical engineering, where we're trying to design a drug or design a protein that has some good behavior that we want to exhibit. So we're given a series of data, and that gives us a pretty basic machine learning problem, where we're trying to find the function optima, which is like the best configuration for the experiment that gives us the best result. And so the basic tool we're using is Bayesian modeling, or like Gaussian process modeling. And suppose that we're given a series of data points x1 through xn, and we observe the function response f1 through fxn. And what we do is we maintain a prior distribution over the f function, and we have access to the likelihood function either via estimate or via some prior knowledge, and we compute the posterior distribution over f. So basically, computer science 101, we have a series of data points. We want to fit this function, a basic regression problem. And one model we can do in a most basic setting is to do linear regression, right? So in a Bayesian context, we place a prior over the parameter space of the linear function. Basically, if f can be parameterized by w1 plus w2x, and we'll place this Gaussian prior on the parameter space pw. And the feature for this function is basically a linear function. It's linear mapping from this Bayes term plus some linear transformation. And we can actually plot the Gaussian process. To animate that, we draw random samples from the parameter space. And corresponding to each parameter, we actually have a line function, right? So the grayish curve is the confidence interval for the Gaussian processes. And we draw random samples in the unit sphere corresponding to W1, W2 vectors. And we can see this function response for the particular choice of the parameters. So now we're using a linear map. And once we observe some data point, we update the posterior using the Bayes rule. Basically, we can compute the posterior over the function parameter space in a closed form fairly efficiently if we have a sufficient small amount of data. Right, so as we can see, like everything done in closed form, it requires this matrix multiplication, which is not that expensive, but there's this inversion which causes some computational issues for this kernel-based or Bayesian inference problems. And now this is the closed form representation for the posterior over the function space. Could be done, again, everything done in analytical form. We have a well-calibrated uncertainty measurement for the response signal, and we can do efficient inference. So for some like real-world problem, maybe the model is not linear, so we can complicate the feature map a little bit more, representing that using a polynomial feature map. Right? So if we expand phi x from 1x to 1 through the third order polynomial, we can have more complicated fitting behavior for the posterior distribution. Similarly, if we extend the feature vector into some other particular form that represent maybe some of the physical insights of the underlying phenomenon, we can have a posterior distribution that has a completely different response shape, right? And we can continue this process, try different feature map functions. For example, if we run for this square exponential with a bell curve, we can have a couple features, nonlinear mappings from input to the feature space, And we run the same procedure, compute the posterior in closed form, and we can get a more, like a smoother response for the function given the data points we have. And now if we keep doing that, increase the number of features from 10, 30, the hypothesis space becomes more and more complicated, but the function response becomes smoother and smoother. In the end, if we have an infinite number of dimensionality of the feature map, that give us this so-called kernels, right? So here we have an infinite number amount of features from the input space mapping to this kernel space. And then for the posterior function, we have an extremely smooth behaved posterior response, and it has this well-calibrated probability measure for the regions that we don't have enough data. All right. So that brings us to the concept of Gaussian process. Just to recap a little bit, we have a Gaussian process is basically a distribution over the functions, where if we take any finite number of input, this function response is actually a joint Gaussian distribution. And with the Gaussian process as the basic tool for inference, we can compute the posterior efficiently, ignoring the fact that we're taking this inverse of the covariance matrix, which is cubic in complexity, but we do have some computational tricks to minimize to reduce that computational load for large data set. I'm going to touch upon that a little bit towards the end of the talk. But for now, if we think about Gaussian process regression, the dynamics is basically as follows. So every time we have one new data point, we add that data point into the training set. We do this inverse of the covariance matrix, and we compute the variances for all other points in our input domain. And so with this guided uncertainty measurement, we can actively acquire data that minimize uncertainty for our model, or actively gather information to minimize uncertainty for our function optima, etc. So that corresponds to different tasks for optimization, active learning, and experimental design. And all right, please.
Can I ask you a question? What is plotted here? Is f of x?
This is the red curve here is the f of x, and the grayish curves are the confidence interval, like the upper bound. So the upper confidence bound and lower confidence bound. It's basically mean plus 3 times.
This is one-dimensional?
This is one-dimensional data. Right. Any other questions? Excellent. Okay. All right. So in Gabor's previous talk, I think he mentioned the connection between Gaussian process regression and kernel ridge regression. So here I just want to be a bit more concrete, just to draw the direct connection between the two. We have the posterior function for posterior distribution over the function f of x, which could be expanded as follows. If we take the negative log posterior, we actually get to this loss function, right? If you inspect this a little bit more closer, it's actually kernel ridge regression in a probabilistic setting. So GP posterior is the regularized least square estimate, which is the kernel ridge regression objective. All right. So that was
that refers to the mean, right?
Yes, the mean function.
How
Right.
about the predictive variance? What would be the frequentist analogon to that? Is that
The means. Okay. So.
right? Because what you said, that is the mean of the Gaussian process.
That's right.
Prediction of the and the predictive variance, is there an analogon?
So we have. So the mean. So the prior of that distribution comes to the is basically here. That's the regularizer term for the kernel ridge regression. And the variance, I would say, is probably an additional, extra benefit for this Bayesian view. Right. All right. Okay, cool. All right. So to set up the basis of the talk, I'm going to show a few examples of Bayesian experimental design using the basic tools of Gaussian processes. But I think before we go there, it's better to set up a general problem for Gaussian process optimization. In particular, here we're looking at Gaussian process Bandit optimization. So the problem is as follows. We're given a set of unlabeled data points U, and we proceed iteratively. For every iteration timestamp t, we're selecting one data point from unlabeled data set, we query the labels, we add the label into the training set, we train the function f by computing the posterior, and our goal is to find the function optimizer, here to find the maximizer, by running through the minimum number of examples. Or equivalently, we can think about we want to minimize the regret, which is measured as, like the expected cumulative regret is measured as the cumulative difference between an expert which performs optimal action at every time step, and the experimental designer which actively seek out for new data which give us more information about the function optima and want to minimize that difference in the long run. Right? I hope the problem setup is clear. And so existing approaches in the literature trying to address this problem in a principled manner include MCMC methods. In this case, I'm introducing this Thompson sampling, which the original algorithm actually arises a couple of decades ago, but the analysis for Thompson sampling for Bayesian experimental design actually showed up within the last decade. So the algorithm works as follows. We have a set of data points, and we compute the posterior over the functions. And so if we maintain this posterior distribution over the functions, we can do posterior sampling. Right? We can sample one point from the posterior distribution over f, and which is represented using this red dashed line here. And at every iteration, we just take the function maxima. Right. So sampling-based approach, very simple, very intuitive, and one can prove that this algorithm is actually going to have a sublinear regret, cumulative regret, which means if you divide the total regret by the time span, you're actually going to converge to 0 in the long run. So this algorithm have a regret rate of square root of t. Divide by t, you get 1 over square root of t, which is converging to 0. A second approach, which is quite popular over the past few years, is this so-called upper confidence bound, like optimism under the face of uncertainty. So what this algorithm does is that at every iteration, it looks into the upper confidence bound, which is the top curve there, and it tries to find a point that maximizes the upper confidence bound, and it does this iteratively. So the upper confidence bound is defined as the mean plus a constant times a fraction of the standard deviation. And that beta t parameter is going to be tuned to give us the best convergence result. But it's not problem dependent. It only depends on the kernel that we're using. Sorry, not even depending on the kernel we're using. But the idea is like if we sum over all the regret over from t equals to 1 to through t equals to capital T, then the sum of the betas is bounded.
So what is mu t here?
Mu t is the mean of the posterior. So the mu t is the mean, and kt x is the covariance between, like it's the variance basically for a particular data point, and we're using the mean plus the standard deviation scaled by beta t. All right. So algorithm questions along this line include, how do we analyze the convergence rate for a Bayesian optimization algorithm? If we're given a more complicated hypothesis space or action space, what are the actions that we should propose in a feasible computational time, and we can still provide some theoretical analysis for the convergence rate. And another particular question that is interesting in the domain of the physical science is how can we incorporate domain knowledge into the Gaussian process model by not just modeling the domain knowledge as a prior, but rather as some informed way for guiding us towards seeking the most informative examples. All right. So to get into like the meat part of this talk, I'm going to introduce one problem that we have collaborated with the material scientists at Caltech, where we're looking at a physical problem where we're trying to design a device, but we have access to multiple computation oracle as the environment who give us feedback. So I'm going to elaborate that a little bit more during the next 10 minutes or so. Okay, so we're looking at a nanophotonics structure design problem. So here the goal is to design optimal material that that is best for like filtering a particular spectra of light, right? So we can view that as a single slit experiment, like light pass through and filter out particular bandwidth of the light spectrum. And so the problem is going to be specifically useful for hyperspectral imaging, which is going to be build a camera, you install that on the satellite, and you take a photo over of the Earth. Instead of 3 channels, we can actually have maybe 1,000 dimensional response channels for a particular image. So we do this hyperspectral filtering and imaging. In this case, basically, for different materials on Earth, we're going to have different separate channels, and we can have much higher resolution response if we can do this filtering job pretty well. So the challenge for the experimental designer is to identify a structure or a physical structure that can encourage the response for a particular wavelength, so that we can filter out the signal in the best way. All right, to make it more concrete, suppose we have a physical device parameterized by a some-dimensional numerical representation, including the spacing of the mirror for the single slit, and the material of the wall, and the height of the mirror, etc. Right, so a light pass through, and in there will be a light transmission response for a particular wavelength. And our goal is to say for a given wavelength, want to maximize the response signal for that particular wavelength, minimizing the response for all other wavelengths in the spectrum. And the material scientists, they come up with this manual handmade fitness function to measure the quality of the response for a given wavelength. And our goal is to design the optimal material that give us the best response for that fitness function. So what we have actually in reality is we have quite a few simulators that can simulate the light response without actually making the real physical device. But the problem is, like, if we do very fine-grained simulation, it's actually very costly. It does give us pretty accurate estimate of the real physical phenomenon, but it is costly. Whereas if we make the simulation coarser and run in shorter amount of time, we still get some responses, but intuitively the response is actually more noisy. So the fundamental optimization question we're dealing with is basically how do we trade off the simulations in different modalities so that we can maximize the information about the function optima while still minimizing the computational cost in the long run. So to set up that in a more abstract way, we have a target function, which is the fitness function. We want to find the function optima, which actually corresponds to this point for the black curve. In the meantime, we have access to a series, maybe one or more auxiliary functions, which is kind of approximate of the original function that we're trying to estimate or trying to maximize. But basically the dashed blue line have some offset, some measurement error when compared with the black line. And our assumption is that the cost for evaluating the dashed blue line is much smaller than the cost of estimating evaluating the black lines. So we model that under a Bayesian optimization framework where we model both the underlying true function and the auxiliary functions as Gaussian processes. And we want to basically calibrate between the two functions as we're doing more and more experiments so that we can maximally use the low-cost functions to gather information about the target function. And once in a while, we check that target function to make sure we're well calibrated and we're actually optimizing for the right thing. So to give you a more illustrative illustration for the algorithm, basically in the beginning of the algorithm, we're trying to get some estimate about both the auxiliary function and the target function. And we would make sure that the functions are well aligned, and we learn the correlations between the functions. And then progressively, we get more information from the coarser estimate about the target function, just to drive down the uncertainty into a particular region of the highest fidelity action space. And then we start query the high fidelity actions. So this is basically a very high-level picture for the algorithm. But when we are actually run the algorithm, it's actually more complicated. We need to decide when to switch to the highest fidelity to make sure we have a pretty simple guarantee for the convergence rate. But that's basically the storyline here. So we have a meta framework where we use the coarse level to get some information, preliminary information, to do a calibration and to drive down the more large fraction of the uncertainty region, and then we switch to fine-grained estimation at the end. So the theoretical question we're interested in, as I mentioned before, is we want to understand the convergence rate. Right? Do we still have this sublinear convergence guarantee when we run this multi-fidelity optimization problem? So to do that, we have to define what is the target object, what is the regret under the multi-fidelity setting. So it's a quite natural extension of the single fidelity optimization problem, where we're just looking to the highest fidelity action, want to make sure that the difference between the oracle, like domain expert, which knows the optima for the target function, and my experimental designer is not too much. So we actually show that in the end using like this intuitive algorithm, we can prove that the regret under this definition is going to be bounded by basically two terms. One term is categorizing the like how much regret we're incurring at the highest fidelity for the exploration algorithm, and also there is some trade-off term for exploring the lower fidelity. So gamma L is the information, the amount of information the lowest fidelity contains about the target fidelity. So the capital gamma is the overall cost for the experiment, and in the long run, if we have a total budget gamma, we divide this regret by gamma, we still have asymptotic convergence guarantee for the algorithm, where we have no regret in the long run. All right, so to give you a brief sneak peek of the results, we basically run this algorithm, which we call MI-Grady, multi-fidelity mutual information Grady algorithm. And we compare with this is the most popular approach that the material scientists were using when designing that device. Particle swarm is an evolutionary algorithm based on sampling. And so the performance of the MI-Grady is actually not that good in the beginning, but it converges like faster in the long run. I should mention that in this setting, like we're given a fixed cost. Like we know what is the experimental cost upfront, and we want to get to the best performance in the end of the experiment. So what we care about is basically the performance in the end. Yes?
Your regret formulation
Yes.
doesn't correspond with finding the best, minimizing your figure of merit for the best thing you found.
Great question,
right?
yes.
So there's some difference there.
Right. That's a great point, yes. We are, the bound we have is for the cumulative regret. And I think the true thing we're interested in is a simple regret, is the best action. We want to minimize the difference between the empirical best that the experimental designer find versus the true best, right? But here, if we have a bound for the cumulative regret, and if we apply the Markov inequality, we actually get, we can convert that into a simple regret. But that's like through this route. Okay. All right. So, so we apply the same technique to a toy example in the domain of cosmological experimental design, where we're trying to estimate the cosmological parameters based on some measurement of the universe. Imagine that we do this cosmological survey, we gather data about the redshift, the fractions of dark energy, and want to make sure that whatever analysis technique we're applying, in the end we're going to get to a cosmological parameter configuration which matches our heuristic about the universe. We want that to be as close as possible, and we want to do that via a fewest number of experiments. So here, the essential problem is kind of similar with the previous material science problem, but I just want to demonstrate the algorithm in a different domain. And the reason why I mentioned that is because right now we have an ongoing project in collaboration with Fermilab, where our long-term goal is to build a self-driving telescope. Basically, we're going to look into a much more complicated action space, which has this hierarchical structure, like what material of the, like what is the hardware we should use to do the cosmological survey, and what analysis technique we should be using, etc. So there is a hierarchical structure in the action space, which we're actually quite fascinating about developing like, principal algorithm to solve this problem. So aside, the problem we have looked at just now is basically we want to use the lower fidelity computational resource to gather information, and the goal is to assist our target decision-making problem, right? So if we think about a similar principle, even if it is not under the context of Gaussian process optimization, we could use the insight to design more efficient strategies for like more general decision-making tasks. Here I show you one example in control where we're trying to do touch-based localization. The setting is we have a robotic arm, and the goal is to open a microwave door. Right, so here I have the illustration for a number of possible configurations about the locations of a microwave in simulation. And we want to make the robotic arm to interact with the environment in a minimum number of times to localize where that green button is. So to give you a quick demo for this application, we have this robotic arm, and on the left is the real-world experiments. On the right is the Bayesian estimate about the hypothesis space, like how many, like that is basically all the possible number of configurations of the microwave. So every time we make the robotic arm, the end effector, interact with the physical environment, it does one experiment and rule out some of the inconsistent hypotheses, and we want to localize a region of the hypothesis space that no matter where the hypothesis lies, using one action, we can open the door. So we just want to do active learning, but we don't want to remove all the possibility of the hypothesis. We just want to gather enough information so that we can act, right? And that actually motivates us to design quite interesting Bayesian optimization algorithms that exhibits this near optimality performance guarantee. So if you're interested, I'll put a link into the to the paper, and I'd be happy to chat offline. All right, so that basically is the first part for the technical discussion, where we want to design efficient algorithms that can leverage different kind of information sources in the most cost-effective way, right? Now I want to switch gear a little bit. I will spend maybe about 10 minutes talking about the other dimension of the problem, where if we have a large action space, like it's so large that we cannot even traverse the action space, how should we even act there? Right, so if there's a combinatorial action space, and we cannot do the greedy optimization, we still want to give informed instruction to the experimental designer so that they can actually carry on for real-world experimental design task. Here the application domain is protein engineering. So the goal is to design wet lab experiments to synthesize, measure, and basically synthesize and measure protein sequences so that we can identify a particular configuration of the protein that exhibits some good property, like response to light, for example. So some of the pioneer work that Francis Arnold from Caltech does is in the domain of directed evolution. So the idea is basically they want to simulate, or they want to accelerate the biological evolution process in the wet lab experiments to engineer new proteins that have particular good property, which would have taken like hundreds or thousands of years in the natural environment. So the mathematical problem is again similar with the previous problem we have seen. We have a sequence embedded in the, for example, d-dimensional space, and we encode the fitness function using some Blackbox function, and our goal is to find a function optimizer via the fewest number of iterations. So the particular problem we're looking at is called direct evolution, where we're given a parent or like a parent protein sequence, and the biochemists, they decide what position of the protein sequence, like which amino acid we should mutate. And then once they have decided these constraints, they put that into the wet lab experiments. They synthesize a large pool of possible protein sequences. And then they randomly sample a field to screen, and they measure the sequences that are of particular interest, and then they add that back into their database to get more insights on what is the right protein to perform next. So what we want to do is that we want to replace that library like pool design problem using a machine learning algorithm, in particular using a Gaussian process model. So as you may see, like the challenge here is like the space of protein sequence is huge, and what the chemists have access to is only which position of the protein sequence that they can mutate. And say they're given a protein sequence of length 4 or 7. There's already, like at every position, there are 20 possible amino acids. So there's already 7 to the 20 possible configurations that they should consider, which is not feasible to traverse. Just to give you like a cartoonish illustration about our algorithmic insights of this problem, we basically aim to solve a batch optimization problem iteratively. So let's say we have enough data right now, like have some data to build our prior. And based on our prior information, we want to design an objective function that measures the performance of a particular set of experiments. Suppose that we do that based on the current prior. Right, so let's say we have a well-defined objective function, which is a set function, and the set function does not have any particular good property like sum-modular or supermodular. It's hardly to identify a function that exhibits such property. So we basically want to identify the best batch at every iteration, so that in the end we're getting a batch that basically hopefully contains a protein sequence that is of a desired property. Right. So our focus is here, like how to solve one particular, like how to optimize a batch, given that objective function does not have the desired property that we want. So what we did for this particular task is we designed a utility function, an objective function, that is neither sum-modular nor supermodular, and we aim to solve that non-sum-modular optimization problem iteratively based on a Gaussian process model. So one thing that is novel for this problem is that even though we know that we cannot solve a non-sum-modular function in an optimal way, we could find an efficient procedure to find a local optima for this particular combinatorial optimization problem. So analogy in the continuous domain, if you think about non-convex optimization, what people do could be like they can decompose that function into a difference of two convex functions, like decompose a non-convex function into the difference of two convex functions, and then they can take they can try to optimize each of the function individually, like optimize the function upper bound, lower bound iteratively to find a local minima or maxima for the particular function. So we have discrete analog. If we decompose any set function into a difference between two sum-modular functions, we have efficient approaches to identify local minima. But the problem for this setup is basically identifying the decomposition of the target function is actually NP hard. So we're actually leveraging the structure of the protein sequence domain to come up with the efficient decomposition of this DS optimization procedure, and we actually have a provably convergence guarantee for identifying a local minima for a particular batch of protein sequences. All right, so I will skip the algorithm details. Actually, this is not so much detail. It's probably similar with the previous slide. I just want to say that we do have a principle of a guarantee for identifying the local minima in polynomial time. to demonstrate the performance of this algorithm, we run this batch stochastic optimization problem on a real protein data set. And we're performing batch optimization, like every x-axis corresponds to one batch of experiments, and the y-axis corresponds to the fitness value for all the samples for that batch that we obtained. So basically, we show after 4 rounds, where every round contains 100 protein synthesize and measure operations, we actually identify a protein sequence within the database that is above 99.99 percentile of the distribution.
Question.
Please.
To make sure the batching here is only because you are picking a site to mutate, or are you trying to optimize picking multiple sites at the same time in the right subset?
We're picking multiple sites to mutate, and they give us a library. And we sample from the library. All right. So I'm going to almost end to the talk. So I'm going to highlight one particular, another application, again, using it in the domain of Bayesian optimization, but it's under a slightly different context. So here we're trying to calibrate a mechanical system. So in this example, we want to calibrate a 3D printing device where we're trying to build a machine learning model to predict what is the temperature at a particular given point given the laser response. The reason why we're doing that is the screen you see here is the trajectory of the laser head when we're doing this 3D SLS, selective laser sintering process. We're trying to melt the powder bed and following some particular trajectory to build a device. And it is crucial during this procedure to maintain a constant temperature in the build chamber to maintain the quality of different layers for that parts. So in this case, we want to adjust the laser power so that we can maintain its temperature. And the adjustment is based on a physics model, which involves solving complicated PDE equations. Basically, we want to replace that using a machine learning procedure that can predict what is the next step temperature response so that we can adjust laser power accordingly. Okay, so physics aside, we want to build a Gaussian process model to estimate the temperature response for a given featureization of the current environment. The challenge here is basically the response of the Gaussian process is spatial temporal. Right? So it's a dynamic system where we need to look into both the spatial domain and the temporal domain. And we're trying to estimate a response curve, which this is like a temperature transfer curve for the physical phenomenon. And we want to use a data-driven approach to estimate this curve as accurate as possible so that we can make the action of what laser power we should use at next time step. So long story short, we use this spatial temporal Gaussian process, and we devise active learning technique, basically telling us at what time we should gather new data to record in order to train a good model that have a reasonable response. So in doing that, we can minimize the storage cost for the costly printing procedure while still maintaining a good performance in the predictive accuracy for the next temperature response. And I want to give you a brief summary and outlook of this basic experimental design direction in general. And I want to highlight a couple of directions that our group is currently actively working on. So we have talked about complicated hypothesis space, which largely draws from the physical insights, what model we should use, and which will go into the prior information and also will give us some structured information about what action we should explore next. we also talk about this action space. For example, when we have multiple fidelity actions and actions that rest in a large combinatorial space, what we should do in order to have an algorithm which is efficient but still have provable guarantees for convergence. Moving forward, one thing that we're interested in is in an extremely large dimensional setting, can we learn a low dimensional representation of the data at the same time as the experimental design procedure? So we know that Gaussian process is not that efficient if we have a large training set, because we need to do that inversion of the covariance matrix, and it also does not work very well in large dimensions because of the kernel constraints. So here we're looking into Bayesian deep learning models, or something close to the well-calibrated probabilistic model using the based on a deep neural net architecture, and that still allows us to do Bayesian experimental design. And another direction is basically how do we learn to make decisions in real time? So many of the Bayesian experimental design tasks require a careful planning. Right? We need to find the best action at every time step, which could be costly. And in the scenarios where making a real-time decision is crucial, we want to make fast decisions. And in doing that, we're trying to rely on the previous learned experience, want to learn to make decisions instead of planning at every time step. Something I haven't touched upon is regarding a rich user interface. So if you think about interactive system where the experimental designer tries to interact with the environment, where environment is a human expert, how can we design actions that actually make sense to the human? And along that direction, we also want to look into this collaborative machine and human intelligence. How do we direct the human's attention into a particular part of space so the human can actively help the machine to conduct more efficient experiments while minimizing the cost. Okay, with that, I will conclude the talk, and I would acknowledge the contribution of the amazing collaborators and also the funding agencies. Thanks.